ask what are these masks about, right? We have done the layout on Cadence, and you need to do it in your project and homework. What is the meaning of adding this mask? And last time I showed you that this is the cross section. What exactly it is? So I copied this video from YouTube, which is presented by, I will stop this one, no sound, because I want to illustrate. Produced by Global Foundries. Global Foundries is one of the major players of the foundry, semiconductor foundry, like TSMC, Samsung, or even Intel. They have the foundry business, right? So here you see that this is just marketing. At the beginning is marketing, but now here, do you see this? This is called silicon ingot. You grow a silicon crystal, which is very large, about the height of this room, maybe very huge, like measure the very heavy, not that high, but like in tons, maybe, I guess, the whole ingot. They grow very high quality silicon, pure silicon, and people say silicon comes from the sand, and that's what you mean. They get all the sand and then melt them down, purification, whatever. Right? Of course, not sand. Right? Sand is SiO2, but then they extract the silicon. Right? They go this high purified silicon, and then what do? Right? They cut it like the pizza. Cut it. This is called. Then each dish, right? This is a wafer. Okay, that's what we talk about wafer. And nowadays the wafer is about 300 millimeter in diameter, or 12 inch, right? So if you ask people what wafer you have handled, you know their age already. For example, for me, I've handled 4 inch, 6 inch, 8 inch, and 18 inch. Then I'm not that old. But some people may tell you that they have handled 2 inch. That they are much older than me. Okay, so they cut the wafer, and then what do? They take one of the wafer, then you start the processing, and that's what I mean by pizza that time. Okay, just like a pizza. Now, when look from the top of the wafer, this is the so-called, don't do that. This is the so-called bird wheel, right? So if I look from the top, this is the bird view, because you're looking from the top like a bird, right? Looking into the city, and that's why this is also called floor plan. Sometimes they call the floor plan when you do the design. But when we talk about floor plan, we think about the whole circuit. And then, if you look in this direction, right, where we are cutting it here, I cannot put my cursor here. If you look at this direction, this is the cross section, and that is what I'm showing here. Okay. So what does it do? Right. So you have the wafer. You just say that this came from the sand after there's some processing. So they are supposed to be chipped, and you see they are all the crystal lattice align very well. This is a finished wafer. One important thing is see this repetition, because they have many dies. They do all of them at the same time. Right, we'll explain more a little bit. Now here is going to show of these people. It is need to be very high quality place. How to say? Absolutely clean. That's why it's called clean room. Right. Now you see each of this is a die. Right, and then you go to your package. So now let's take a look. You zoom in, and then your feature, your stuff, your circuit supposed to be there. Now, in particular, show this lithography process. It drops some photoresist, which is liquid, and then what it does is spin the wafer very fast, so you form a very thin layer of coating. And after you form the coating, you see on the top, this is the mask. This is what you design. For example, I say I want to draw some hole here, 3 holes. This becomes a part of this mask. Then you have a laser light source going through this mask, going some optical system, and you form the image on the photoresist. And the photoresist are light sensitive. So for those open area, we call it develop. You either harden it or dissolve it, so that after this process, you transfer the pattern to the photoresist. Do you see this? And because all this, maybe this square, will get light, and then it become dissolved, right? Just chemical reaction, photochemical reaction. And then you put in the water, solvent, then those parts will be dissolved. Then you only have the pattern left, like this, okay? Now, after you have this pattern left, then so what? Here, what it's trying to do, I think, is ion implantation. It shoot a lot of atoms, ions, from the implanter. For example, boron, phosphorus, arsenate, whatever you choose. Then you see that those opening area is going to receive the atoms. Let me show you again here, right? Those area that is open, this is silicon, will receive the atoms. But those on the photoresist, they stop at the photoresist. So as a result, this part is not going to get any atoms, right? So that's why I can selectively form the N plus and P plus region by doing photolithography. Any questions? Make sense? Okay, then this is a finished product, right? Now they handle the wafer. Now this is what I believe this is the annealing. So in the past, now you implant the atom, you actually make it is like you damage the crystal somehow. The atom phosphors, they sit not in the right location, so they are not activated. You don't get the electron and hole you want. You can do annealing, means that bring it to very high temperature, and then they will just wiggle, eventually sit at the right place, just like cooking or whatever, right? So you can put in furnace. But now for advanced technology, we actually use laser. This is azimuth laser. They use the laser to heat up to very high temperature at very short time. Maybe 1200, 1100 degrees C for 1 millisecond. I don't know what the technology is now. The reason is to avoid the dopant to diffuse too far, right? And that's why you see it is scanning. You use the laser to scan through the wafer to activate them. Now you see this red are the dopant originally, right? They are not at the right place. They are all at this space. They are not electrically active. Now after annealing, they go to the right place. Do you see that? They substitute into this cross section where used to be the silicon. Make sense? That's called substitutional doping. Okay, and then they are activated. They will conduct electricity, right? Well, right. This is another step already. Look at it. It forms a layer, right? It can be so-called atomic layer deposition. Nowadays the technology is so good. Applied Materials, Lam Research, they produce this tool. They deposit layers of atoms, very well controlled. So this is not doing implantation. You see they deposit conformally. This is the key word, right? And then what do? Then they also put in some, I guess this might be copper or oxide actually, or oxide. I don't know what they're trying to show. But the main point is this. You see that if you try to deposit something on top of it from your cooking experience or pizza making or cake making experience, you know that you are going to have some very uneven surface, right? That is not good for the next layer lithography if it is not even. I won't explain now. So they actually have something very interesting. It's called chemical mechanical polishing. This chemical mechanical polishing called CMP is to help you polish all those uneven parts. Then your wafer becomes very flat. Then you can continue on the next layer. And that is a very important invention because in the past we used aluminum as the contact. In late 1990s, almost 2000, right? IBM demonstrated they can use so-called dual damascene process to use copper. Copper has very low resistivity, but it cannot be manufacture using the traditional aluminum method. So you cannot etch them. So in the past, you deposit the metal and then you form the photoresist, and you etch those you don't want, right? You use some chemical reaction to remove them. But copper doesn't work. You don't have such chemistry that do effectively. But what they do is that you use the dual damascene process. You electroplate the whole wafer with copper, and then you CMP. So what I'm saying is this. You only want to form metal in this groove, right? You only want to form metal line here. What do? They just deposit copper everywhere, right? Try to take a look. It is everywhere. And then you just keep polishing, and then stop at outside the groove. Then isn't that you form the copper lines already? That's called CMP, right? And then these are the interconnects. Right, so these are some important process, but you see that they all related to lithography. This depends on how you draw it. I did not draw the metal one here. Here is a metal one. That will be a part of this, right, if you finish it. And of course, this is a 3D. Here you remove the oxide and insulator. You see this huge network of interconnectivity, which is now the bottleneck of scaling, because what we call the parasitic resistance and capacitance are dominating the performance of nowadays chip. Now, what are they doing here? They finish the fabrication process. They are dicing the wafer, right? Let me show you again. They cut it. Of course, this is artistic work, right? So you don't really cut it with 4 blades, but you cut it, and then you have a chip. Each of these chips, you need to package it, and then you go to your computer, iPhone, or whatever. Now, so you see that you have one wafer, large wafer, but you make many chips at the same time because you just use lithography, whatever, all in one shot. Okay? So if you have a large wafer, you get a lot of dies. And at the same time, if you have a small chip, you can get more dies at the same time. If your design is small, then you can have many chips. So that actually affects the profit margin of a company. Make sense? Any questions? Now, go back to take a look, combine with what I said. I hope you have this idea if you didn't know about this before, okay? Great. Yeah. Okay, so that's what I